This is Cambridge Central Mosque in the UK, designed by Marks Barfield Architects, and it is a beautiful building. Today, we're going to be making it in geometry nodes. Not the whole thing, just the timber structures, but that is going to be challenge enough. There's a lot of very specific, very precise control that we're going to be enacting today, so it is quite technical, but I think you'll enjoy the process. Huge thanks to today's sponsor, GarageFarm.net. They're an online rendering service aiming to help artists and studios meet tight deadlines by drastically reducing their rendering times. The service is easy to use, doesn't require any IT knowledge, and is affordable. GarageFarm.net offers up to $50 for newly registered users and 33% discount for Blender rendering. That's a great deal, and if you need any support, their team is available 24/7. It's not just Blender either, they support all major 3D apps on the market, so no matter what you're using, they can help speed up your rendering process. So if you want to save time and speed up your projects, go and check out GarageFarm.net, links down in the description. We're going to be meeting them again later on in this video to make our final renders for this project. This is the final outcome for today's tutorial. This is our Blender model where we have created the pattern. It's the pattern is actually fairly straightforward, more straightforward than you would probably expect. We're going to be working in Blender 3.6 and we're going to be breaking this down today. This is quite an involved tutorial. We're going to be working through making quite a lot of nodes, as you can see here. We're going to come out of here with a couple of useful tools as well, just to, scale up your workflows. I will be using Blender 3.6 for today's session. You don't need to be in 3.6, 3.4 or 5 is going to work for you fine. It is basic index manipulation, curve workflows, all basic stuff that you've been able to do since like 3.0, 3.1. So all of this should be fine whatever you're using. Let's look at the pattern, because from this angle, it looks quite complicated. From above, when there's a lot of them, it also looks not simple, right? So let's just lay this out flat and have a look at what's going on, break it down a little bit. So this is what the pattern looks like, laid out as a single tile. So this is what we're going to be making, and then you can simply array it at the end. It's very straightforward, actually, surprisingly so. So the first thing that happens is we create this simple layout, and all this is actually just a grid of parts like this, right? It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a 12 by 12 grid, and we simply have to remove alternating sections of 2, right? So that's fairly straightforward. So we can create this grid, great. And then a little bit more complicated, we can create this rotated grid, which is a grid which just has some of the diagonals removed. But again, not actually too difficult to make. And then the last thing that we need to do is simply fill in this center section with the spokes. And this is a little bit more involved. It's not just index manipulation. There's a little bit of checking the direction of curves that we need to do, but essentially it is not too hard. We can simply instance our lines and pin them into the correct positions. If you were doing this in something like Grasshopper or AutoCAD, like a more proper architectural 3D software, then your process might be a little bit different. The way that we're going to do this is the geometry nodes method, but it will be simpler in the future as geometry nodes builds up its tools. Now, it's not just about creating this pattern. We also need to work out how we can go about actually creating this sort of rotation, because it follows the funnel shape perfectly. So another thing that we need to do is we need to find out how to tilt curves to align to a vector so that we can transfer from the normals of another mesh. That is the long and short of it. And then just to finish off, I'll do a little time lapse of me building up the rest of the room. Again, probably largely with geometry nodes. And then we're going to create a render with GarageFarm. Let's jump in. I'm in Blender 3.6. Go ahead and add a plane or cube or whatever you want. This is just a container. We're never going to see it again. So new geometry nodes, rename this one to Cambridge Mosque. Rename my object as well. I'm going to go ahead and just delete that group input. Do not need it. And I'm going to collapse that right hand side so I have more space. There we go, ready to get going. So first thing that we want here is going to be a grid node. If you're not used to the new menus, it's under Mesh, Primitive, Grid, or you can just search for it. Size of the grid is somewhat immaterial really, but I'm going to put mine up to 11 by 11. It's going to make things a little bit easier later on. So 11 by 11 with 12 vertices means that I have a can see that lines up nicely there. I have 1 meter spacing. So this is going to be important when we want to do a little bit of extension, because then we know that we just do things in terms of meters. And if we want to scale this at the end to be a certain size, for example, if we want to match the actual building, then we can simply scale everything down once we've worked out the actual pattern. So nice and easy process, just saves us a bit of a headache. First thing we wanted to make was this regular horizontal and vertical pattern. So that's what we're going to do first. It's actually a fairly simple workflow. So I'm going to just go ahead and take a geometry, operations, separate geometry, which is going to allow me to essentially delete one half or the other and give me this selection in inverted. I'm going to be separating geometry based on edges, and the way that I can split these is based on edge direction. So I can find which ones have an X aligned direction and which ones are Y aligned. That could be my mask. So let's grab a mesh, read. We're looking for edge vertices like this, and we're going to find the direction from one to the other. I'm just going to subtract. So that's a vector math subtract one from the other. Next up, we want to add a compare, which is going to be set to vector, direction, equal, because we're just going to find out when it's equal to something. And we want to set our angle to 0, just to make sure that we're doing exactly the angle we're looking for. Let's plug this in here, Shift-Alt-click on that to view the output. And let's try 1 in X, that's not going to give it. Let's try -1. There we go. So these are all of our horizontals and verticals now separated. Hopefully you can see this. Let me try. We're doing a lot just in edge land today, so let's turn on thick lines and hopefully that'll help you see things a bit better. All right, we have our 12 lines. We now need to remove these 2, and then we have 2 on, and then we have 2 off, and then we have 2 on, and then we have 2 off. And we start with 1 here. So 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. This is our mask. How do we create a mask that looks like this? Well, it's all about index manipulation and a little bit of maths. So it should be fairly straightforward for us to do. We are going to just take, let's just take our verticals for now. Before we continue, let's make sure that we are framing and naming. Always important to stay organized here. So Control J, F2. This is going to be our split H and V. There we go. You will thank yourself when you come back later to a node tree and you've commented it properly. Let's take our verticals here. We are going to be just doing a delete geometry. Set this to edges and view the output. All right, I'm going to move this down so I can zoom in a bit. I'm interested in the index, so I'm just going to search for that. If I want to plug this into here and I want to use this to debug, so let's put this through an equals, and I'll just plug this in. So I can see this bottom one has come off, and then the next one, the next one, next one, next one, next one, and so on. So we're just counting up in this direction and then this direction. So nice and easy for us to work this out. So what I now need to think about is like, what is the wavelength that we're working with here? Remember, this was on, so 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. So this is a repeating pattern of 4 lots of one whole vertical line. So we want to find out how many points, how many segments are in this line, and there's 11. So if I take this down to 11, you can see this is the next line. So 0 to 10 is on this one. That's 11 segments, and we have 4 of them. So let's try something here. Let's add Shift-A, a utility math node. And this is going to be doing a modulo, which is how we can repeat by a certain number. Let's try 44. There we go. So now, if I do 44, then we are repeating this deletion in the same place there. So that's what we want. We now have a repeating pattern with the correct wavelength. So now we can use equals on our compare node to speed things along a little bit. So it saves us a little bit extra work. If we set our equals to a float value, then naturally we get an epsilon. So this is kind of like a bracket. If I was to set this to 10 with an epsilon of 2, then I'm going to get 2, like 10 subtract 2 and 10 plus 2. So epsilon is your bracket on each side, plus or minus epsilon. Because I want to delete from the middle, let's think about what our index would be. So the index right in the center of 44. So 0 to 43. Halfway around there is going to be like around 22. So let's try 22, and let's just increase this. This should be probably an epsilon of 11 because we're taking off 11 on each side of 22. It looks like 22 was a bit high. I'm going to assume, therefore, half of 43 is going to be 21.5, and that's correct. So that's going to give us that correct fall off that we're looking for here. All right, these are our verticals, nice and easy. We also want to just plug these into the horizontals. Same mask. There we go. And let's just join these back together. So the reason that we split these up before is now these lines and these lines are not connected. They don't join at this vertex. They are completely just like straw overlaid on one another. And that's kind of what we want, because we're going to be turning these into curves. And we want them to be predictable, basically. We want to be able to control where one curve is and another curve is not. And so there we go, that's the next step. We're going to turn these into curves. So Shift A, we're going to grab a mesh, operation, mesh to curve. And there we go. Let's name and frame. We're just going to grab these nodes here up to our deletes, Control J. This one is going to be our remove line 1 and 2, there we go. So I'm sort of indexing from 0 there. So we're leaving 0 and 3. All right. So then we've turned them into curves, and we're going to do something now with these. And it's important that we turn them into curves, because what we need to do is actually extend them. So this pattern demands that we add half a meter, and that's why we set this to a meter spacing. So it demands that we add half a meter of extension beyond this. Because when you have another one of these over here, you actually have this kind of tram track in between each of the patterns where you've just got a little bit of connection, and it's also repeating this spacing over here, right? So we need to extend our curves. This is actually super easy as well. So what we're going to do, because we're just doing a straight extension, we don't need to think about curvature, we don't need to think about really anything. We're just going to create a tool for extending splines by a set amount. Let's do a set position. And with this, we're going to be offsetting some multiple of the tangent and only at the endpoints. So let's add this offset here. We are going to put in a scale here, vector math scale, and we're going to be scaling the curve tangent. There we go. So you can see that all of these are now going in the direction of their tangent. We're just offsetting the whole lot. We don't want to do every point along the curve. We're just interested in doing the endpoints. So let's add an endpoint selection node, and let's just select the first and last points. There we go. Now the distance that we're going by, the tangent is normalized. So just anything that we multiply this by, that is the distance. So we would want to go like 0.5 for that half meter. However, it's all moved in this and this direction. I want the start point to go in the opposite direction. So let's put in a switch here. And this Boolean is going to be another endpoint selection. So I'm only selecting the start point this time, 0 endpoints. And we're going to be doing something in here. Now this, I could just put like 0.5 and minus 0.5 in here. But this is actually quite a useful tool, and we're going to be using it again later. So rather than needing to duplicate the nodes, let's put this into a node group, Control G, and I'm going to press N, go to my group. Let's rename our input here to curve and our output to curve. Just, it's important to be explicit in what a node group is used for. And again, you'll thank yourself later. We're going to be taking our switch, and rather than minus 0.5 and 0.5, we're going to go 1 and minus 1. And we're going to use this as a multiplier. So let's add a math node set to multiply in here. And then we can just simply control the distance with this multiplication. If I plug this in directly, I'll just get a standard value socket. I want one with meters. So I'm also just going to steal a socket from a grid primitive. Here we go. And I'm just going to call this one extension. Now this is not a proper extend curves node. It's only going to do like a linear extension in a specific direction, and it's not creating a new curve, it's just moving the point. So it works for our benefit here, but if you have something more complicated where you have curves, this is not what you need. Perhaps we'll do that in a different tutorial, but for now, this is what we are going to be using for today. Rename the node group to extend. And there we go. Our extension is going to be 0.5. So this is our main grid. And clearly there's a little bit more going on here, but we will kind of break into that as we move forwards. Let's for now have a look at creating our diagonal grid, which is going to sit on top. We are going to be using the exact same starter grid. This is very important. And we're going to be creating our diagonals by joining across each face, just like this. And then we're just going to use these lines, so we're going to ignore everything else. The workflow here is pretty straightforward. Just add a triangulate node, like this. There we go. Now we have some diagonals. You can set this to shortest diagonal, or you can go it to fixed alternate. They're both going to do the same for you, really, just in different directions. It's fine for us to just use one of these, so fixed here, and then we're going to delete everything in the background. So the way that we're going to be doing this is by proximity. We have all of these edges already, so let's just add a geometry proximity node. We're interested in the proximity to edges, and we're interested in where the distance is equal to 0. So let's be deleting edges, like this, and there we have it. That's all you need to do. All right, so this is one set of our diagonals, and I also now need to delete some of them. If we come back to our main version here, what we can see is that we are deleting one line that we keep, and then here's the next line, that one's been deleted. Here's the next line, that one's been deleted, and here's the next line, that one has been deleted. So we keep 1, delete 3, keep 1, delete 3, keep 1, delete 3, so on and so forth. So once again, we have a repeating pattern that has a wavelength of 4, and it's going to be 1, 0, 0, 0, 1, 0, 0, 0. So once again, we're going to be deleting. We want to keep this one, and then 0, 0, 0, 1, 0, 0, 0, you get the idea. We just need to understand what our indices are doing so that we can make sure that we're deleting the right sections. So let's come in here, let's grab an index node. Let's delete everywhere that is equal to this specific index. And there we go. All right, so this one here, which way is it going to go? Right, so we're running up the side this time. It's not going along the edges, it's not going horizontally, going vertically. And what this means is just the same in the vertical axis here. We want 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. So again, wavelength here of 4. So we can just do modulo index 4. And then we're going to delete everything which is not 0, 1, 2. So we're going to delete everything that is not equal to 2. So got our index modulo by 4, and we're deleting where it is not equal to some value. There we go. So that's immediately, that is the right spacing. We want it, let's change this to integer because we're dealing with integers, not equal to 2. And there we go. This is the shape that we would expect. I'm going to just be a bit lazy here. I should really just do this on the opposite direction, but seeing as I've already got this, and I can just transform it 45 degrees, no wait, 90 degrees in the z-axis, and this is going to give me my other one, and I can simply join these together. Now I've got the whole shape that I need, and once again we're going to be doing a mesh to curve on here. So now we have curves, and again it's important that you have made these separately just so you don't end up with that interconnection on the points there, so that our curve, when we have curves, this is a very explicit spline. It's not contaminated with any cross direction. Now, once again, we need to be extending these so that we get this corner match out here. This is actually a little bit more interesting. So let's duplicate up our group and put it up here. This doesn't reach where we want it to reach. So what do we need to do here? Well, the reason it doesn't reach is because what we have is a 45-degree line coming down. We have a distance here of 0.5. And therefore, because this is 45 degrees, we have 0.5 over here as well. we're looking for this extension length. So this is going to be x. This can just be dealt with the square of two sides. So a squared plus b squared is equal to c squared. So therefore 0.5 squared is 0.25 plus 0.25 is going to be equal to 0.5. So the square root of 0.5 is equal to x. So you can either just write square root sqrt of 0.5, and that'll take you to an exact point. Or if you prefer using nodes and keeping things a bit more explicit, you can add a utility math node set to square root 0.5 and plug that in like that. That's going to work for you. So this looks a lot like the pattern that we have here, but again, we're missing the middle section on the one that we want. So let's grab these ones together. These are our diagonals. And let's grab these ones. These are our, I'm just going to call these ones even, I guess, even lines. So we've got our diagonals and our evens. They're all coming off the original same grid. This is always important. Make sure that your inputs are narrow and your outputs are narrow, and you can do as much as you want in between. It's all going to stick connected. So the next thing that we want to do here is I want to split our curves into the ones that meet the middle. So anything which comes through this section, we need to split off those curves. And it's the same for the horizontals. We want to split off this inner cross. And for this one, the inner cross. So let's just try this. We're going to grab a separate geometry. And we're using splines now, so we've converted these to splines just to make our lives a bit easier. So in terms of indexing, we now have things like, well, actually, let's just have a look. Let's see what our indexing is. Let's grab an equals node. Let's grab an index. There we go. So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We are interested in just the ones that go through the middle. So let's see which ones they are. We've got 0, 3, 6, 9. 0, 3, 6, and 9. So what I can do is just modulo by 3. That should work fine. Let's just grab a math node, modulo by 3. And there we go. Now I have the ones that cross the middle and the ones that go the rest of the way. And when we modulo by 0 and put this into a selection, instead of 0, 1, 2, 3, dot, 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 we have 0, 1, 2, 0, 1, 2. And then because we're passing this into a Boolean selection, it's thinking this as 0, non-zero, non-zero, 0, non-zero, non-zero. So that's how we can just use that directly without a compare node. Just saves you a little bit of time there. So this is splitting off the ones that go through the middle. And then we're going to basically do the same thing. So separate geometry down here. But this one's a little bit more complicated. I'm actually going to take off the outside square and just be left with the cross in the middle. And then I'm going to split that cross. There's a reason for this. As we move forwards, we're going to be doing a little bit of hacking with the fill curve node. It's going to just save us a bit of a headache. And I just don't want to have the outside square when we do that. We're going to be using an index and a modulo probably, because it's going to be a repeating pattern. Actually, let's just have a look at our indexes directly. So let's delete equals. So there we go. We've got 0, 1, 2, 3, 4, 5. So 0, 5. And then we have 6. And we have 11. So 0, 5, 6, 11. We can think of this as like a repeating pattern through the middle, where it comes like this shape, and then we just want the bottom parts of this. So what we're going to start off with here is we're going to grab a modulo, so math modulo, set this to 6. If I plug this in, let's go to my inverted. There we go. So now I have two edges. So basically where this equals 0. If I wanted to find where it also equals 5, then I could either do two compares. I could do equals 0 or equals 5 with a Boolean math. And that would be like the most proper way. Or we can use a compare float using the epsilon, or we can do a ping pong just the same. Let's actually do a ping pong just because it's a bit of variation. So let's add a ping pong in here. If I set this to 2.5, then that's going to be the full thing. Why does 2.5 work? If you think about your graph, you've got point at 0, 1, 2, 3, 4, 5, and then you've got 0, again as the next section starts. And we want to basically come up to a point and then down here, and we want to hit 5. And then 0 again is going to start here again, right? And go up. So what is this point here that is halfway between 0 and 5? Yeah, that's 2.5. So that's why we're doing this ping pong up to 2.5 and back. And then that becomes our mask. And once again, wherever it equals 0, that is the Boolean. So it's just thinking of this in terms of 0 and non-zero. So let's frame this up. This is our outer square. That's there. And then we're going to add another separate geometry, Alt-P to drop it out of that frame. And now I want to basically split this into an outer section and an inner section. So once again, we're thinking about what is going to come through this central part where we want to put the spokes on that we can then pull down into that column. So separate geometry here. So we're going to ping pong again just for fun. In fact, let's do it the other way. Let's do it with the compare. In fact, let's do it with 2 compares. So then you'll have had all 3. You'll have had this float epsilon method. To do it over here, you'll have had the ping pong method. And this time you can just have the 2 booleans from the compare. So our wavelength here is going to be 4. So add a utility math node. Set your modulo to be 4. There we go. And then we can plug this through a compare node. Set to integer because we're dealing with indices. So at 0, we have this. And at 3, sorry, we have this other corner. So then we just want to use a utility math, Boolean math, to find out when either or is correct. So now I just have my inner and my outer like this. All right, so far so good. Let's frame this one up as well. Control J, F2. This one is going to be separate. I'm just going to call this one crosses so that we can think about it. And let's keep moving forwards here. This one is our separate diagonals. All right, cool. We don't really need to do anything to the outer section, so I can immediately join these 2 together. So that's fine, because these are basically done. They're as they are. What we do want to do, however, is do something to the inner section, where we have these sections crossing that middle. So we're going to grab another join geometry, and we're going to pull up the other one. So this is everything that comes through the middle. And I basically want to delete everything in here. Everything that fits inside this circle, we're going to delete. And then we're going to build spokes manually. So, do we have any way to do this easily? So when you're dealing with splines, let's just grab a delete node here. And let's say we're deleting edges. That's not going to come up with anything because, well, there's no edges in a curve. All we have is splines, and I want to delete specific segments. So the way that we have to do this is convert it first to a mesh, so CTM for curve to mesh. Then we can delete specific edges, and then we can do a mesh to curve on the other side once we're happy with it. So how do we find these? Well, we could base this on the vector length from basically the position. That would work fine. That would give us a nice circle in here. But how do we know that radius? And if we change anything else before, like if we change this grid over at the start, that radius is going to change. So we want this to be dynamic. And fortunately, we already actually have something that is basically giving us this space already. Like if I draw this circle in here, very rough, I apologize. Then you can see that that actually is the area I want to delete. So I want a circle that is as big as this square. If I grab a fill curve node, then I can create this square. So that's a good start. Now I want to basically find a circle that fits in it. So I want to use a bounding box node on here. So let's pull off a BB for bounding box. But if I look at this, you can see it extends all the way out. So first of all, I need to trim off these bits. So let's create another tool for this. We're going to be deleting wires. So a wire is basically an edge with no face next to it. That actually gives you a hint of how to mask it. So let's grab a mesh, read, edge neighbors, any edge where the face count adjacent to it, its face neighbors, is equal to 0 is a wire. So I can then use a geometry operation, delete geometry, set this to edge, plug that into my mask, and now I just have the middle section. Let's grab a bounding box so I can find out how big it is. And then because we're dealing with radius and this is centered, I can just find one axis of one of these outputs. So let's grab this, separate X, Y, Z. So now we've got this X, we can basically use this to offset a hypothetical circle on here. In fact, let's preview this a little bit. Let's grab our curve, just so that we have something that we'll actually draw with our overlay. Let's grab a position node. If I view this, you can see the positions directly. And if I add a utility vector math set to length on here, it's all looking pretty white. If I was to do something like a map range just to make sure that we could see this, then you can see that we have this intersection and it's a smooth gradient coming outwards. All I'm interested in is where this gradient is greater than our value. So this is all looking white at the moment. The reason is because, okay, so we've got a -2 there. Let's just make sure we're using the max value. There we go, that's a bit more sensible. So this is what we're interested in. So the bounding box max, wherever this value is greater than, we now have a mask. We can use this to delete edges from our curve to mesh node. So let's go back onto here. Let's delete that viewer. Let's grab a delete geometry, set this to edges, and we're going to plug this in like so. I need this to be inverted, so let's go with less than. And this is pretty good, but we've got this kind of connection here and it's a little bit too like boxy in the middle. We can make this a little bit better. I want these to feel that these sections are the same length. I want this to kind of come through like that instead. And the way that we can do this, we've got our curve to mesh. Let's just use a subdivide curve, or subdivide mesh, sorry, which is like a simple subdivide node. Level 1, yeah, level 1 is fine for this. So just one level of subdivision. Then we've got our delete geometry, and then we can go back to the mesh. So mesh, sorry, back to curve, mesh to curve. And now we have our curves again. All right. Before we move on, let's take our delete wires and turn this into a node group. So Control G. I'm going to leave this as is pretty much. I'm going to rename these outputs to mesh because we need these to be meshes only, won't work with curves. And then let's rename this one to delete wires. There we go. I'm going to frame all of this up. This one is going to be called delete center. And then we can move on to the next part. And the next part is creating the spokes. And this is actually fairly straightforward, but there's something to be learned here about flipping curve direction and understanding which ones you need to flip. So what I want to do, I've got my curves. I'm going to be instancing on points some curve lines. Now I don't want them to go everywhere. Now I'm not interested in how long they are either. So I can just leave them like this for now. I want them to only be instanced on the starts of the curves. So the reason is, if we have a curve like this and a curve like this, when these join together, I want the curve factors to be kind of going up in the same direction. It's going to help with the indexing. I'm not sure how it works in geometry nodes at the moment, because we basically, to join, we have to do curve to mesh, merge by distance, mesh to curve. At some point in the future, there will be concatenate curve nodes and things like that. But yes, just for now, that's our process. But essentially what I want to do is I want to make sure that I'm always instancing on the start of this curve. So let's grab an endpoint selection node. Let's delete the ends. Oh dear. So I need to flip all of these curves that have started around the outside. I need to find out which direction they're going in and flip them based on that direction, whether it's away from the center. Now I can't just pick the direction, because these ones need to go in this direction and these ones need to go in this direction. Obviously, based on the indexing, these were originally one continuous line, so it makes sense that they go the same direction all the way across, right? But all of these ones I'm going to need to flip. And the way that I can do this is by checking whether or not the curve tangent, which is in this direction, is in a similar direction to the position vector. So if these two directions are the opposite, like they are here, then I know that these need flipping. In this one, the position is like this, and the tangent is like this. So these ones are more similar than these ones. So that's how we're going to do this. Let's find the curve tangent. Nice and easy. And let's just view on here. All right, so obviously these are in pairs, and that makes sense. These ones are exactly aligned to X, these ones are exactly aligned to Y. These ones are 45 degrees. Let's find the position. So just kind of as we would expect. Now if I do the dot product between the tangent and the position, then I'm going to get some information here. And you can see that some of these are going one way, some of these are going the other way. So this becomes a mask. We need to do a little bit more work here. So this position, the tangent is normalized. So for us to compare against it, we need the position to be normalized. This just means to have a length of 1. So there we go. Use a vector math normalize. Still gives us the same output. That's good. And then I'm not going to leave this up to the gradient chance. I'm going to do an explicit compare. So I'm going to find out where this is greater than 0. And there we go. It still looks the same, but that's how we have it. And now what we can do is simply use this mask to flip or reverse curves. Like this, and we can drop that on there. Now let's have a look at where our curves all are. There we go, they're on the outside, that's fabulous. Let's do a less than instead. There we go. So now we have this mask. Name and frame, Control J F2. This is going to be flip curves. That's descriptive enough. Okay, then we're instancing on the start points. That's good. That's where we need to be. And then we want to actually work on these curves. So let's realize them. Drop that on there. And from now, we need to do a little bit of setting position. So let's come in here as well, set position. And I'm interested in not touching, well, I need to do something first to this. So the curve line, for a start, it needs to be of length 0, because I need the start and end to be on the instance position. Secondarily, I now need to make a selection of just the start point. So if we have our curves, our outer ones going in this direction, I want my inner ones to come like this, which means I want my start point to be the piece that I'm now manipulating in towards the middle. Hopefully this is making sense. So I've just made that selection on the start. So now we want to move these points towards the center by a specific distance. And we need to work out what that size actually is. And once again, we're going to be referring to our original grid. We want this all to be kind of proportional to what's going on. So we want to be setting the explicit position, but first of all, we need to find out what the radius of the circle that we're creating is going to be, so that we can actually set to this radius. The way that we're going to do this is using our inner circle. So we're going to create a circle that fits in this and actually is smaller than this. So we're going to go for half the size of this square. So once again, let's use a fill curve, but this time we're using our inner cross here. So this is giving us this plane. We're going to use our delete wires node just to make sure that we've got rid of that outside stuff. And then we're going to be using a bounding box node. So just BB for bounding box. There we go. And now we have information about the min and max. Let's take our max through a separate XYZ. It's going to give us our values, and we can plug this directly into a mesh curve. So, sorry, a mesh circle. Let's grab our X into a mesh circle. Here we go. All right. Let's plug this into the radius, and there we go. So how many vertices do we need? Well, we're going to need to count that. And then what is the radius? Well, we want it to be half of the width of that box. So let's also just add a math node set to multiply by 0.5 or divide by 2. So how many points do we actually need? Well, we could do this dynamically, which feels a bit overkill because this is never going to change. So what we're going to do, let's just hover over here. Let's have a look at what we've got. Instances, we are computing 16 instances. So let's make sure that we have 16 points on our mesh circle. Another thing that we need to do is we need to rotate this, because right now we have a point top, side and bottom, and we actually want these to be coming off diagonally like this. So we just want to rotate this until we have the facet facing the axes directly. So let's use a transform node. So let's do 360 degrees in a circle divided by, we've got 16 points, so let's start with 16. So that's one full thing. Let's divide this by 2. There we go, that's what we want. So 11.25 degrees. Cool, all right, this is our center. We now just need to use this to position the ends of our curves. But a couple of things. So let's just move this across because we have it now. This is our radius coming off like this. Let's put this onto a reroute that we can rename. This is our inner radius. And we want to use this to set the position of the end of our curves here, or the start of our curves. How are we going to do that? Well, we have the current positions of them, and we want to basically make it so that it's this position if that position was only the radius away from the start. So what we can do is we can take this position, we can normalize it. So let's take our position node. I'm going to plug this through a normalize. So now this has a length of 1. If I plug this into the position node, then you can see, there we go. Let's get rid of that offset as well there. So now we have a length of exactly 1. And then let's multiply this, or scale it again, by our inner radius. There we go. And now, if I just join these two together, you can see that that's really close. I mean, it's perfect in terms of the actual radius, but some of our points are not quite touching, and we need these to be perfectly regular when they come down here for them to sit nicely on the floor. Nice easy way for us to do this is geometry proximity. So let's take our transformed circle through a geometry proximity. We're interested in the points, and let's take another set position over here. Once again, we're taking the selection of the start of the curve, and we're going to plug the position from our proximity node into that one. There we go. That's just going to neaten that up like that. So you can see there was a slight change on those diagonal ones, and now it makes a perfect little sun. So I don't actually need to see that circle. It's just being used as a guide. So let's frame these ones up. Control J, F2. This one is in our inner circle. Great book. This here. These are our spokes. So F2, spokes. So now what we can do is we need to actually join these to some other things. Let's join these up to our reversed curves. Let's just bring this over the top here. Join those together. There we go. That's looking great. These are all... No, they're not. I was going to say they're all meshes, but they're not all meshes. This one is a curve, and this one is a curve. So let's do a curve to mesh, because I need to join these together, because I want to smooth out this. Basically, to do that, I have a couple of options. I could either do a curve to mesh, merge by distance, and then subdivision surface. Is this going to work? It is. But I kind of hate that. So what we're going to do instead, because we don't want to be dependent here, is we're going to fillet the curve. Now we've merged them, we've joined the curves together. Let's turn this back into a curve, so meshed curve. And then we're going to add a fillet curve on here. So let's do a poly, go for like a high number on our count, and we can just increase this. Now, okay, here's another thing. With a fillet curve, you can go beyond your available geometry. So you could limit the radius, and then it's going to basically be set by when it runs out of geometry. It's kind of like clamping overlap in a bevel modifier. But if we want this curve to be a bit bigger, we're going to need to do something with our curves. We have a lot of points right now and we don't use them at any point. So what we can do is we can resample our curves just when they're joined here. So let's do a resample curve. Let's resample a count of 2. So each curve is just a curved line. So we're going to do just a 2 count resample. So it's going to have a start and an end and a start and an end. So then when they get joined together, we have almost unlimited space for this. Basically, we have all of the space until the end of the curve. I'm going to still keep on limit radius just in case, but that's pretty good. So you can set this as smooth as you want. I might give mine a little bit of an angle. Cool, this is looking great. Let's Control J, F2. This section is our bevel corners. And then we can join this together. What are we doing? Okay, over here, we've got our join geometry. I'm just going to use one of these as like a bus. So I'm going to take this all the way down here. But let's keep going. I'm going to join up into it. Look at that, that's so cool. So this is our pattern for the roof. Basically the pattern's done. We don't need to worry anymore about creating more pattern. The next thing that we need to do is give this some 3-dimensionality. It is completely flat. So what I want to do is create a mesh dummy of the, we're going to call it a funnel shape, that we can then raycast onto. So I could do this all just by like manipulating it up, but I need a little bit extra from this funnel mesh. I need the normals, because when we want to have our curves rotate nicely to follow that surface curvature, we're going to be manipulating it based on the normals of this funnel. So it's just going to save us some time later, making things easy for ourselves. So what I want to do is create a circle that has a radius that comes out to here. So we're going to basically, because I'm going to be raycasting onto this, I need to make sure I cover the whole area all the way into these corners, right? And it can be just down to this inner circle size here. So to do this, we need a cylinder that we can dynamically change the radius of the top and the bottom independently. All right, so how big is our inner circle? Well, that is this multiply here. So we can use this to set our radius, but how do we make this in the first place? How do we make a circle that has a hole in the middle? And also I need a lot of resolution in here because I need nice smooth curvature. Well, actually fairly straightforward. So we're just going to skin a curve. So let's grab a curve primitive line and a curve primitive circle. And I'm going to do a curve operation curve to mesh. There we go. Now I have a cylinder and I can set the radius of these points independently. So let's grab a set curve radius like this. And this radius is going to be set with a switch node. And I will use just the index. So a curved line only has 2 points. So it's just going to be 0 and 1 on the index. Now I can set my top and my bottom independently of one another. That's exactly what I want. Now my smaller one is the curve radius. Here we go, the inner circle radius. Great. And the outer one, let's do a little bit of Pythagoras here. We have a main grid. Let's make sure that we can actually see the size that we need. And let's delete all of this. There we go. So where we're coming out to is 1, 2, 3, 4, 5, 6. So we've got a 6 meter in this direction, and then we've got a 6 meter in this direction, and this hypotenuse length here, this is the radius of that larger circle. How do we find this and how do we make sure it's tied to this actual object? Well, we can simply take a bounding box of one of these. Let's just bring this down here. Plug this through a bounding box node, BB for bounding box. There we go, that's the full size. We can take our min, separate x, y, z. And then once we've got one of our axes, let's actually do off the max here, we can work out the hypotenuse. So what are the nodes for this? Well, if this is giving us a 6, and I need to know what 6 squared plus 6 squared is, and I actually need the square root of that to give us that hypotenuse. So a squared plus b squared equals c squared. So the square root of c squared gives you c. So this is the square root of 2 times 6 squared. So let's just do that. So we've got 6 here. We're going to square it, or do it to the power, sorry, power of 2. We're going to multiply this by 2, which is the same as adding it to itself. And then we're going to do the square root of this over here. And this is going to give us our second radius for our circle. There we go. Let's make sure that we have enough points on our resolution here. Let's make this nice and high res. Let's maybe go up to 200 is probably fine. And then I need to resample this curve as well. So let's just, before our curve to mesh node, let's add a resample just to make sure that I can set a goodly amount on here. So I'm just going to go until these outer ones are square. There we go, 30 does fine. Now I'm not worried about the conical shape here. We're going to be controlling that Z height completely procedurally. Let's just frame this up a little bit here. Control J, F2. This one is our outer radius. And this one is, including that frame, Control J. This one is create funnel base. There we go. So we've not created the actual funnel shape yet. Next thing I want to be doing in here is I want to control some of my Z heights. Let's grab a set position. So down here, first of all, I want to make this flat. So let's take our position and I'm just going to put this through a vector math multiply. And I'm going to go 1, 1, 0 as my multiplier. So that's negating the Z axis. Now we have this completely flat. Why didn't I just do this with a flat curve to begin with? So if I shrink this down, as I come towards 0, you can see it flicks off. That is the problem. So when you have a curve with 0 length and you resample it, no matter how many points you tell it to have, it will only have 1. So if you want to have lots of points, you just need to keep some verticality. It literally doesn't matter how much you use. You can have it super tall. This set position is going to flatten it. As long as you have some verticality, this will work. We've now negated the Z-axis. We are then going to offset the Z-axis manually. So now we've got it to 0. We're going to now offset it in the Z-axis. So combine X, Y, Z is what we're going to need here. Let's find the length of the vector as we come out, because I want a gradient that is going to come out towards the edge that I can then manipulate with a float curve. So I need a 0 to 1 gradient. Let's take our position, and it's important that we use the flattened one here, because before it was flattened, this position is also going to take into account the Z-axis. I only want to know how far away it is horizontally. And so we need to do this with the negated Z version. So let's take a length node on here. Let's say vector math. And then if I just plug this into my Z, you can see that we get a nice linear gradient coming out from 0. We want this gradient to actually start right here. So we want it to already be moved out. So we're just going to remap this. Let's use a utilities math map range. And our from min is going to be the inner radius. So once again, we're going to take our inner radius here to our from min. Great, that's perfect. The outer radius we're going to control a little bit, but it's going to be based on this square root of 72. So if I just put that in there, then this comes up like so. All right, so it's not actually going to be the full amount. It's going to be probably half. So let's just add a math node set to multiply 0.5. And there we go, we're good. So now it comes up to half the radius and then it goes out flat along the top. We want this to be flat because we want each of our tiles to be dead flat around the outside and then drop in only in the middle. We want to control this more than just how we have here. So we have a 0 to 1 range now. Let's put this through a float curve. And then on the other side, we're going to map range it from 0 to 1 to some new range. So 0 to 8, perhaps, maybe 0 to 10, something like this. So you can see that this shape is becoming something. So once we've got this funnel shape, we can actually start shaping it quite easily. We could just basically drag on our float curve until we have a shape that we're happy with. The cool thing as well is this shape here, while you can just control it very easily with this, because you want to be careful about this angle, and we're dealing with a 0 to 1 range, what we could actually do, so we can actually just use a math node set to power. when we're dealing with this. So if I set this to a higher power, then you can see that we can actually pull this up a little bit. We are getting a lot of stretching there, but you get the idea. Because we're working with a 0 to 1 range, we have a lot of control that we can do with it. So I like using these float curves because they give you, so much control. You can do whatever you want. Also, it's just a bit of manual artistry. We just have to be careful how we blend in at the top there, just to make sure that we do get that nice and smooth. There we go, something like that should be absolutely fine. I'm not coming in too steep at the bottom because I don't want to stretch this out too much. If I turn back on the wireframe, you can see that we're already losing a lot of that topology. We have loads at the top, but it's quite sparse down here. If you want to remedy this, just increase your sample counts. Okay, something like 200 in that as well. That's going to be absolutely fine for this. Cool. All right. So next thing that we want to do is frame all of this up. This is the funnel depth. There we go. I'm going to turn off my wireframe again. And now we can actually use this. So let me just change the color of this just to make sure it's not getting mixed in with everything else here. This is specifically a guide mesh. Absolutely nothing to do with the pattern. So let's grab our pattern on here and we want to raycast. So let's grab a raycast node. We're going to be raycasting in the positive Z direction from here up onto that surface. The target geometry is going to be the funnel that we just made. And we want to do some things up top here. So first thing we want to do is set the position. So geometry, right, set position. Hit position can come up here. Okay, that's looking pretty good. Pretty good. This is a bit rough. We need a lot more topology to go in here. So after our join geometry, let's use a resample curve. Let's use a length of like 0.1. Just gives us a lot of points that we can work with here. Makes it a bit smoother. I think this actually comes in a bit too far here. I'm going to increase this multiply. So that's the multiply coming off the outer radius that sets the limit for where this comes to. I just want to make sure that these curves here get some of that nice curvature to them. If I go out too far, then we're going to come right to the edge that we don't want, but just in the middle here. Do you know what? I've forgotten something actually. We have an outer frame that I have not re-added back in. We have this over here. Let's just grab it and pull it down here. So Alt P to remove from the frame. Let's grab another one. We're going to be coming across. And this one as well can join up into that main join. I can't believe I forgot that. There we go. Now we have the full pattern, including that outer box. That's important. Definitely want the outer box to get the proper effect. So then we're resampling, then we're setting the position. There we go, that looks much better. Great, I have just increased that multiply for our maximum displacement in the Z-axis to be 0.6, just to make sure that we're getting a nice curvature all the way around. And now what I want to do is, let's just go ahead and skin it. Let's do a proper curve to mesh with a profile and make this into like a proper actual mesh at last, because there's definitely more for us to do. So CTM for curve to mesh. Let's grab a quadrilateral. There we go. We can fill curve. I'm just going to turn off my thick lines again. Let's go back to default. I find it draws really weird for the cavities. So let's reduce our width and height here to something a bit more sensible. So I'm going to go around about 0.2, 0.4 for my size here. That's pretty good. We can see this is all smooth shaded when you do a curve to mesh. So we're also just going to do a set shade smooth to turn that off. So this is looking great. However, all of our curves are using something called minimum twist, which means that they try to not spin around and not twist too much as they come around here. So you can see that we're pretty much upright along the top. In fact, it's doing an excellent job of being upright here. However, it does mean if I go above, you can see that we've got a lot of weird twisting going on inside here. Although this looks very cool, like a little square in a square. But it's not what we want. We want this to be perfectly aligned to the normals of the mesh. Because like these cross ones that dip down in the middle here, This is not a nice junction. Really, we want everything to be aligned in this direction. There's a bit of maths here that we've got to do. So hopefully at some point, geometry nodes will have an align tilt to vector node. I think that would be a good idea, but for now we can make our own with a bit of vector math. So we need to align, well, first of all, we need the normal direction. So let's grab a normal direction on here. I need to raycast the normal direction and store it on the mesh before this set position, because once it's on the mesh, there's a bit of a risk really when raycasting that you've gone through it because of the sampling, but then you're raycasting to infinity. So let's make sure that we are capturing an attribute for the vector just before here. And we're just capturing that on the points. So that is fine. So we're capturing the normal of our raycast surface, of our funnel. Let's go back to our final nodes here. So I need, in between here, in between our set position, our curve to mesh, I need a set curve tilt. And I need to work out what this tilt is, because I can take a look. So if I just use the viewer, here we go. So these are our normals. And everywhere that the normal is the same, the tilt should be pointing towards it. So we need to work out basically what the current tilt is. And if you don't know this, if you have a curve, it has a tangent, but it also secretly has a normal. And that normal direction, whatever that normal direction's z is, its up direction, that is basically the curve tilt, right? Wherever this is around here, we can use this to work out what the curve tilt is. And you can also use the tangent and the normal to create your binormal if you use cross product. We're actually going to be doing all of that just now. If you just want to jump straight ahead of the curve and have it done, if you have ETK, you can use your curves, align tilt to vector, align tilt to vector, plug this into your tilt, plug your vector into here, and there you go, that's going to work for you. But we want to learn how to make this ourselves. First thing that we're going to need is information about the curve. So let's grab our tangent as well as our normal. So these are the two nodes that we're going to be needing here. We're going to be also creating the binormal, which we're going to use a cross product to do. So cross product of this and this is going to be our binormal. So I can just name that. Now we're also going to have the actual input vector here. So let's grab this for a reroute just so that we have it named. This one is going to be the surface normal, like this. And we also want to find out what the cross product of the tangent and the surface normal is. So by doing this, we will have our curve tangent, which will have a normal here. And then separately, there will be some other vector that goes off in some other direction. And this one is our surface normal. So this one's the normal, this one's the tangent. If we find out what the cross product is of both of these, then what this will do is it will create two vectors which are exactly rotated around about your tangent, and they can be normalized. We make sure that they're normalized, and then these two can actually be compared. So this is how we do it. We're basing this all around the tangent, like this. And we're using the cross products to create these secondary vectors that we can compare against one another using vector math. You don't really have to know how vector math works. Honestly, I couldn't sit down with cross product and dot product and do it for you on paper, but I do know it's sort of intuitively what it's doing, right? And that is all that matters when you're doing this kind of problem solving. You really don't need the in-depth stuff. So I know a lot of people get questions about maths. You can learn it intuitively based on your use cases. So that's the best way. So I want to normalize these to make sure they have a length of 1. So we're going to use another vector math node set to normalize. Now these are two comparable vectors, and to compare two vectors, to see how similar they are, use a dot product. A dot product will give us the result of cos of an angle. So it will give us, if something is in exactly the same direction, it will give us a vector of 1. If something is in the opposite direction, it will give us -1. And if something is in 90 degrees, it will give us 0. So if that's our dot product, then we can find out what the angle is if we use an ACOS, so inverse cosine. So I can just use a math node for this, set to arc cosine or inverse cosine. Let's make a bit more space down here. And now we have our actual tilt. Let's try plugging this into the tilt. So generally this has worked. Actually, this has worked surprisingly well. Yeah, this has worked fantastic. So this is kind of all the nodes you need. However, you've got to safeguard yourself because sometimes things will be flipped. And the problem is, well, basically when you get into that second part of that cosine graph, all of this, you can't really compute from your cosine because it's coming like it will have already chosen the first part. So if it's actually needing to rotate more than 180 degrees, this will not suffice. So you need to also be able to rotate backwards. And we do this by safeguarding ourselves and switching, and we will basically inverse this within that 360 degree period. Okay, I'm saying words now. Let's just actually do it. Let's grab a vector rotate node. We want this set to axis angle, and we're going to be taking the cross product of the surface normal and tangent. So this is one of our secondary vectors that we computed that was comparable. We're going to be plugging this in as our vector. The center is at 0. The axis that we want to rotate around is the tangent. So now what we're doing is we're basically rotating this vector that we have around our tangent, and we're going to just try rotating it, rotating that tilt value by the value that we just computed, by that arc cos. If the result of this is not equal in direction to our binormal that we computed, then we have a problem. Because what should have happened is we compared the angle between these two, and we found out what that angle was. If we have just rotated this one by this angle, then it should align to the binormal, unless it is greater than 180 degrees out of phase, in which case we can set our direction is not equal, angle of 0, epsilon of 0.01, that is fine. So if this is no longer equal, which it should be exactly equal, then we can use this with a switch. We're going to be doing a switch float based on this mask. We're going to be taking our arc cos into the false. And if it is not equal, if this is true, then we need to inverse this. So we have a value somewhere along our cosine graph. Maybe it's here. And what we actually wanted was this one. And to do this, we just need to basically subtract this distance from 2 pi. So we're just doing that. We're going to take this, we're going to put it through a subtract, and we're subtracting it into the second socket. We're subtracting it from 2 pi or tau, T-A-U. Plug this in up here. And this is our switch. Let's make this into a node group, because this is our like a line tilt to vector, Control G to group it together. We have our input vector, and I'm also going to add an offset just because it's useful to have an offset in these things. Let's grab an add here. We're going to grab that group input as well. Just duplicated that across, and I'm going to set this to add 0 to begin with. And this is going to be our tilt angle on the output. So this is our offset on the beginning, and on our outputs, this is our tilt. There we go. Align tilt to vector. That is the name of this node. Okay, so we made a bit of space there, but we don't need it anymore. Let's join this up. So this is not looking promising anymore. So why was this, why was it working before but not now? Let's tab in here, let's have a look. The reason is, okay, so we need to just invert this vector rotate, and then it should set this back to 0. There we go. So all it was that vector rotate needed inverting, and now it's going to work great. With mine, I've actually also added another math node in here just to set an offset by default. This seems to rotate by 90 degrees out of phase automatically, which you don't always want. In fact, you almost never want. So just put pi by 2 in here. So add by pi by 2, before your offset, and that's just going to make sure that you have that 90 degrees phase offset to begin with. That's looking great. I think this has worked perfectly. All right, final stretch here. Let's tab back out. So we've got our curve tilt, that's great. And what I'm going to do, I'm going to move my curve to mesh right to the end because now I want to create an array of these. The actual building has maybe 4 or 5 of these across, maybe 4. So what we want to do is just create an array based on that size. Let's do this dynamically rather than eyeballing it and making sure that it just looks correct. We're going to do this properly procedurally. We're going to do it based on bounding boxes. So I'm going to be, and also another thing that's important actually just before I carry on, if I go into 7 up here, after I've skinned it, this point, right, this line that comes down, after it's been skinned, you are offset by half of whatever your profile width was. Obviously we don't want that to happen. We don't want the next one to be starting over here and having a little dead space. We want to make sure that we are properly coming off the correct location. So to do that, you just basically base it on the size of the curve. That's going to work fine. So take your set curve tilt. We're going to put this through a bounding box node. There we go. Here is the size of our column. We need to find the actual dimensions of this so that I find what the period between columns is. So let's take our max. Let's subtract from it the minimum. This is going to be now the proper dimension of our bounding box. And I'm going to put this through a separate XYZ. And then I can use the X and Y into my size X, size Y of a grid node. So let's plug these into a grid. There we go. And let's view this. Great, that looks perfect. Let's plug some integers onto here because I'm going to need these as controls. So integer X, integer Y. If I set both of these to 3, for example, then the size of this hasn't got bigger. Let's make sure that we are multiplying by 3 on both of these. So I'm just going to multiply and multiply like this. Now this is a bit of a trick really, because this is still not correct. If I just do an instance on points, where the column is my instance, and that mesh grid that we just made is our points. Well, now we've got a bit of space in here. Now, the more integers I add, the closer these get together. And the relationship is actually, we just need to multiply by the integer -1. The reason for this is basically if you have a grid like this, we have 2 lots of space, but we have 3 instances. So all you got to do here is just take a subtract, put this onto your integer, subtract 1. I'm just going to collapse that and rename it just to keep it a bit neater here. Rename that to -1. I'm going to do the same down here with this one, and there we go. Now they line up nicely. So you see that double beam in the middle? That's really important just to make sure that these are shaped the way that you want them to shape. A little bit of love. Let's give these bevel modifiers. Come into here. Let's add a bevel. And before this, we need to make sure that we realize instances just to make sure that bevel wakes up. So instance on points. And then let's add a realize instances node on here. There we go. And I'm also going to turn off fill caps because I don't want to break that connection. Let's just go for something nice and small, just a little iris on there. Okay, this looks great. We can add a set material node if you want something like that. And you can add yourself a simple material in here. And let's come off our scene world. There we go. Obviously very simplistic for the materials here, but you get the idea. Let's make sure that we are framing and naming everything as we go here. So this section down here up to our realize instances, Control J, F2. This one is going to be our array. This last section is the skinning or the mesh. And this section here is position and tilt. Control J. Position and tilt. There we go. If you're still with me, thank you so much. That was a lot of nodes to go through in a tutorial. The next section of this tutorial, I'm basically going to be working through building a little bit of the rest of the scene up, right? This is a building, so it would be cool to have some more of the building around it, and then we can do a render. So we're going to be working with our sponsor for today's session, which is garagefarm.net. They are an online rendering service for artists and studios, and we're going to be learning how to create a render of this beautiful mosque with GarageFarm. So I'll see you after the time lapse. Welcome back. I have finished as good as I want to get with this little exercise. I just put together the one foyer room here, and I set up a few little bits. So we've got little details here and there, just kind of the floor, some cabinets, and it looks pretty good. Go into material preview here. It's a bit slow in cycles, to be honest, and I am intending to use fog and also render in animation. So we're going to be rendering with GarageFarm, and it's going to be pushing it pretty far, I think, hopefully. We're going to be rendering 400 frames of an animation as the sun passes over. Now for a preview, this is totally fine in my viewport, but if I was wanting to actually render this animation, that means that I'm multiplying my render time by 400, which is a lot. So we are going to go through setting up GarageFarm. I've never used it before, so this is going to be my true and honest first impressions of using GarageFarm.net. The link in the description is going to take you to Blender Render Farm, and this is where we can get our 33% off, so it's only 55 cents per hour of GPU time. And as well, we're going to be getting a $50 free credit here. So let's start our free trial. You're going to be prompted to set up your profile, so I'm going to go ahead and do that. So once you've made your account and you've signed in, you'll be greeted with this page. And one of the great things I'm seeing immediately is this trial period where you get the $50 free credits. All of the features are enabled and there are no watermarks on your frames. Some other services will watermark your frame during trial periods. This, you get the full access to the render farm. You do have a limit of 10 render nodes and 30 jobs. So you get a little bit of a walkthrough here. Let's just go ahead and jump in. Let's go up to downloads, and it told us to download the client. I am on Windows at present, so I'm just going to go ahead, download for Windows. To begin with, you get thrown some preferences to set up. So whether or not you want to automatically download finished frames, I've said yes. Download folder, I've just pointed this to the current project just to make sure that my files go straight into where I've saved all the blends and all of the process files, all the textures I've used. Temporary folder, because I'm working specifically in this folder, I'm going to keep them all together. I'm going to keep this in English. I'm going to save my settings. Log into your GarageFarm account. Make sure that you log in. This is how it's going to send it from your local PC up to their servers. When you first open it, you're going to be thrown onto the plugins page. We're going to be using Blender here. So let's install our Blender. It's going to ask us to shut Blender. So let's make sure that we've saved and quit. Let's retry this. So I just wanted to navigate to a Blender version. So I just pointed it towards my 3.6 install. And this is all now plugged in. So let's go ahead and just reopen Blender. So now I've got that Render Beamer add-on installed in Blender. I'm going to go back to my mask here. Let's go into rendered view just to check that this is exactly what we want. I'm going to skip to frame somewhere we have a nice bit of lighting. And I just want to do a test render. So let's go up to our render drop down, our render menu, go to Render Beamer, and let's beam it up still frame. So before deciding to render a full animation or full render resolution still shot, we recommend running a test render first. You can render every nth frame to estimate the cost, or lower resolution to check if the scene renders correctly. I'm just interested in seeing if the frame renders correctly, so I'm going to go ahead, click OK. Scene is being prepared. There we go. Let's have a look at Render Beamer here. So it's uploading, it's 120 meg, so it's just going to take a minute to upload here. Once uploaded, it's going to ask you to confirm that you want to submit this as a job. I am going to say yes. There we go. It's taking us to our account on the website where we can set this up a little bit. Not doing a frame range, we're just doing a specific frame, 1920 by 1080. We're using 3.41. Output path is here, that is correct. Output file, the extension, I actually want this to be PNGs. I know I could do EXL for easier post-processing, but this is unnecessary for something like this. Preferred hardware, let's just use the standard here. Don't need to worry about advanced settings. And there's a single camera, so I'm just going to render this one. Render device is going to be GPU optics, that should be fine, and the strips, that's fine. Cycles path tracing samples, I'm going to set this to 500, and then I'm going to submit. There we go, we're going to proceed. So that was successful. Just to download the render there, I went across to my Downloads tab on the client, refreshed it, this got the link downloading. So here we have it. Here is our render from inside the space. Once you're happy with the results that you're getting out of Garage Farm, we can go ahead and just render the whole sequence. Or try to anyway. So I'm going to go back to the beginning. I'm going to save here. I'm going to go into Render Beamer, and I'm going to beam it up animation. This time we want to tell it to do an animation, so we're going to turn on the frame range here. We're going to keep most of the rest of this consistent. Let's keep EXR for now. Just going to give us a bit of more opportunity to color grade after the fact. We're going to be rendering our camera, and I'm going to reduce this. I did 500 before. I'm going to go for 200 frames, 200 samples this time. Let's submit our job. One thing I really enjoy about using render farms is that while this is downloading still, it's still rendering, still downloading, I can actually still just use my computer. It's not using my computer at all. Just out of curiosity, I want to render a couple of frames locally just to see what kind of time saving I'm actually getting, because I do have a fairly fast PC and it's just kind of an interesting comparison. Render farms are something that really scale when you're doing animation. And let's just render out a full float EXR just as we are doing, 1920 by 1080. And this time, let's just render out 10 frames just to see how long it can take. Around about 2.5 to 3 minutes per frame for me. So let's say 2.75 minutes times 400, because that's the number of frames that we've got. That's 1100 minutes, which comes down to 18.5 hours. So even that is still going to be me running my PC all the time, 100%, for a full day. Whereas using a service like Garage Farm is going to allow you to do the same thing in around about an hour, give or take. So around about 20 times faster than a top-end PC. If you're working on, for example, a MacBook or a laptop, then the benefits that you're going to see from using a service like this are orders of magnitude higher. Hope you've had fun learning about using geometry nodes to create Cambridge Central Mosque. It's a beautiful building, and I think it's hugely useful and powerful, and I definitely want to see more people getting into architectural design using Blender. I think the tools are there. We just need more people to pick them up. Lastly, a huge thank you to garagefarm.net as well for sponsoring this video. Don't forget that if you use the link down in the description, you're able to be getting a 33% discount as a Blender user, and also that's $50 of startup credit for your free trial. That's it for today. I hope you've had fun, hope you've learned something, and I'll catch you in the next one.